going to take a look at log properties and a lot more. We're going to do this through the lens of a practice quiz. First, let's take a look at some of those properties that you really need to know here. So first up is the log of a product. These are very similar to exponent rules. What I want you to know to look for is you're going to be looking for any log of any base and the idea that the product or something is being multiplied inside of them. That means we're going to be able to split it apart to an addition problem. And again, the base doesn't matter as long as all the bases matches up. The next thing to look for is when you have the log of a quotient, so the idea of a division problem. And if you see this, you're going to be able to break this up to a subtraction of two separate logs. So what we're doing is we're expanding, and this greatly simplifies equations or helps you solve them later on, especially when you enter calculus. The next rule comes across a lot, especially in chemistry, is when you have the log of a base to a power. Now that power up here basically is going to come outside and you're going to be able to multiply it. So if it's a squared, it's going to be multiplied by 2, and you're going to have 2 times the log of that value there. And when all else fails and you get stuck in a log problem, if you can reduce it to a basic log, you're going to be able to rewrite it. And the way we rewrite logs is you take a look at whatever the base is here, b, and you're going to raise it to the power of y, and it's going to equal the x. Some people refer to this as the log loop. So it's going to be the base to the power of the answer is equal to the value. And the whole idea behind this is a logarithm is actually an exponent. So you'll notice that it says the log base b of x is y, and here we see that y is the exponent. So let's go ahead and take a look at a practice quiz, and you can follow along with the one that's attached, and we'll see how we do with each one. So the first up, it says to rewrite in exponential form. So what that means is we're just going to use that log loop again to write this as an exponent without the word log in it. So we see the base is 2. We're going to raise it to the -3, and it's going to equal x. And it's just saying to rewrite, so we're not going to solve anything. We're going to do what it's asking. So it's going to be 2 to the -3 is equal to x. If we really wanted to solve it and do something extra, go a little bit beyond, we can simplify what 2 to the -3 is. We should know that 2 to the -3 means 1 over 2 to the 3rd, which is 1/8. Over here, same idea. We're just going to practice this. We're going to take that base of 3 and we're going to raise it to the x power. So we're going to have 3 to the x, and that's going to equal what we call our argument, whatever's inside that log. We can put parentheses. So it'll equal 1 over 27. And again, we're not looking to solve for x here because it's simply said to rewrite. But if we want to go the extra mile on this one, and we may see this again later, 3x, we can rewrite 27 with a base of 3. So that would be 1 over 3 to the 3rd. And we should know using negative exponents that that's equivalent to 3 to the -3rd. So now that the bases here match up, that means the value in the exponent, x, must equal -3. So we do know that x equals -3. Next type of problem is going the other way, is when we see something in exponential form, can we write it as a logarithm? Now the way I like to start with this is I just take a look at whatever is in the exponent. And we're going to start with that, and x is going to equal, that is a logarithm. And then we can see whatever the base was attached to that, base 4, and then our argument is going to be whatever the answer was, 1 over 32. And again, we're not being asked to solve for this. We may see this again in a future problem. Over here, we have a little bit more going on. Here we see our exponent. There's more than just an x. It's x minus 3. So we're going to write x minus 3. That is our exponent. And that is going to equal the log with a base, and the base was e, was down at the bottom there. And again, the argument is going to be 5. Let's simplify this a little bit more. So we're going to get rid of this -3 here, and we're going to add 3 to both sides. And when there's a log involved, I like to keep addition or subtraction in the front so we don't confuse it with the log argument. So we're going to have x equals 3 plus, and you should know that log base e is the natural log, which we simply write as ln of 5. And there is our final answer. And again, for these problems, again, we're just doing the idea of that log loop. And I'll write that one more time here. Log base b of x equals y means we're going to do b to the y. And that is going to equal x. And here we were just going backwards, so you can use those back and forth. And let's just identify that answer for you. So far it's pretty basic, just rewriting using that idea. And we're going to do the same thing here. Now it's saying to evaluate, so we do want to simplify as much as possible. And it just says log base 27 of 9. What this means is that 27 to some power is 9. And it's hard to see that for many people. So what we're going to do is just write that this is equal to x, and that's going to be what we solve for. Now we can use our little log loop. We're going to take that 27 to the power of x, and we're going to say that is equal to 9. Now to solve this, what we need is like bases. So we're going to reduce 27 and 9 to the lowest base we can. And in doing that, we're going to have 27, we should know, is 3 to the third. And that's going to be to the x power, and 9 is 3 to the second. So here we have power to a power. So we're going to say 3 to the 3x, that's where we multiply, equals 3 squared. So now that we have the bases matching up, that means we can set the exponents equal to each other. We're using a property here. Some people say they drop the bases. I like to say we're equating exponents is what we're really doing. So we're saying 3x equals 2, which means that x is going to equal 2/3. Next up, we'll do the exact same process. We're going to say this is equal to x. And again, what we're answering is 4 to some power is 1/32. So we're going to do 4 to the x, and that's going to be equal to 1/32. Again, we want to reduce these to match up. You know, how are 4 and 32 related with the base? Well, 4 to some power will not give me 32 using whole numbers or any type of integer. So we can kind of think our way through it, or we can reduce them both as much as we can. So we know that 4 can be written as 2 squared, and then it's going to be to the power of x, so we can say that is 2 to the 2x. 32, we should know, is equal to 2 to the -5th. And it's always nice to have a little chart written down of the powers in case you forget. So we're going to have, oh, it's +5th, got ahead of myself. So now 1/2 to the 5th will end up equaling 2 to the -5th using negative exponents. So now we can equate those exponents at 2x is equal to -5. So that means in this case that x is going to equal -5/2. So it is okay when you find the log of a value, it can be negative, all right? But we can't log a negative number because of domain restrictions, and we'll see more of that later. Now we're going to start to apply those log properties from the beginning, possibly. Or we're just going to look to simplify where we can first. So in the first one, I want to combine these and use the log properties, but notice we have a log base 3 and a log base 7, so I can't use those log properties. So now I'm going to think, all right, log base 3 of 81, this answers the question 3 to some power is 81. And if I can't see that clearly, we're always going to write things down. So log base 3 of 81, we're going to say equals x. And again, there's the log loop. 3 to the x is equal to 81. Reduce 81 as much as we can using a different base, using a common base of 3. So 81 is 3 to the 4th, so x equals 4, which makes sense. So we know that 3 to the 4th power is 81, and that's what this answers. So now we have 4 minus 3 times, and then we're going to look to do the same thing here. Let's see if we can do this one without rewriting. Log base 7 of 49 answers the question, 7 to what power is 49? Oh, well, 7 squared is 49, so the answer here must be 2, because again, it's the exponent that it's answering. So here we have 4 minus 6. Our final answer here is simply -2. The next example uses the idea of inverse, where we have log base 6 of 6. So those two values, a lot of people say cancel each other out, they undo each other, different ways we can write this, but basically log base 6 and the base 6 to a power undo each other, leaving us with just 2x. ln, which is log base e, undoes base e to a power, so those two will undo each other, leaving us with just 3 plus x. Can't lose that plus sign in the middle. And we can simplify this a little more, recognizing that we have 2x plus x, so that will be 3x plus 3, and there is nothing else for us to do because we don't know what this is equal to, so we leave it as an expression. So these are some problems I really like because it helps you understand the idea of breaking down logs and how we can expand things. So we're told that log base 3 of 4 is equal to a. So that means somewhere in these problems, we need to find log base 3 of 4. And also log base 3 of 5 is equal to b. So again, we're looking for something with log base 3 of 5. And our answers are going to be in terms of a and b. So first up, we have log base 3 of 100, which is not 4 or 5, obviously. So we can find different ways to break 100 down. So first thing I always think of is I'm thinking of money, 100 cents, 4 quarters, so 4 times 25. So now I can see how a 4 is going to come out of this. And 25 is also 5 squared, or we can think of it as 5 times 5. I'm going to go with the 5 squared for this problem. So we can rewrite 100 as 4 times 5 squared. Now, you should recognize we have the idea of multiplication, right? So the log of a product. And if you reference the rules we started with, that's going to break down to an addition problem. So log base 3 of 4 plus log base 3 of 5 squared. So we have the log base 3 of 4 that we were looking for, so we can replace that with the letter A. Now here we have the log of 5 squared, so that power can come out front, again using the product power rules. So that would be 2 times log base 3 of 5. And we know that log base 3 of 5 is b, so we can replace that with a b. So our final answer for this first one is simply a plus 2b. And that is the expression rewritten. Up here looks a little confusing because it says 1.6. I'm not sure where that comes from. So when you come across these, realize sometimes we can rewrite things using fractions. So 1.6 is also known as 16/10, which reduces to 8/5. I feel a little bit better about that. So now I can say I have log base 3 of 8/5. Same thing. So I can use the log of a quotient, which is going to equal the difference of those two values. So log base 3 of 8 minus log base 3 of 5. So I feel good about that log base 3 of 5. I know that's b, but here I have 8, and I want a 4. Well, I know I can use 4 times 2, so let me try this out. Log base 3 of 2 plus log base 3 of 4, because 2 times 4 is 8. Let's write that in there. Show a little bit more work. Minus the log base 3 of 5. Now I need to do something with this log base 3 of 2. I'm just not sure. I know there's some kind of connection. So I'm going to go back up here and mess around with this log base 3 of 4. Realize that 4 could have been simplified to 2 squared. So we can rewrite that as log base 3 of 2 squared, and this 2 can come out front using those rules. So now we have that equal to a. That 2 is gone. So log base 3 of 2, if I divide by 2 over to that other side, is a over 2. So we can replace this log base 3 of 2 with 1/2 a. And then here we have log base 3 of 4, which we know is a, and minus log base 3 of 5, which we know is b. 1/2 a plus a is 1.5, or I'd rather say 3/2 a minus b. And there is our final answer for that one. Next up, we see we have log base 3 of 5/9. Seems like we can apply those properties right away. So I'm going to write log base 3 of 5 minus log base 3 of 9. I feel great about that log base 3 of 5 because I remember up here it's just equal to b. So I can replace that with a b. But now I have a 9. I have nowhere to get that. So what I need to recognize is the base of 3 is related to 9. Remember, this answers the question, 3 to some power is 9. And if we forget that, we can apply our little log loop. So our log loop here would be 3 to some power is equal to 9. And we know that must be 2, or we can rewrite 9 as 3 squared, and we can see how it matches up. So we're going to have b minus 2, and there's nothing else we can do, so we are done. Now, part D, notice it says log base 4 of 25, so those are different bases. So we need to use our change of base rule. Now the change of base rule says that if we have log base, we can go with any base here, so I'm going to say base b of x. is equal to log base, any new base, so I'm going to just say c of the x over log base c of the b. I like to visualize this as I can do the log of x over the log of b. And I can replace it with any log, natural log, log base 10, or in our case, what we want to do is we want to use log base 3. So using the log base 4 of 25, I can just rewrite this as log base 3 of 25 over log base 3 of 4. So I just went log 25 over log of 4. Now log base 3 of 25 we saw earlier is the same as log base 3 of 5 squared. And that 2 can come out front. This is what we do a lot, over log base 3 of 4. So we have 2 log base 3 of 5. Remember, log base 3 of 5 was simply b. So we're going to have 2b. That's a 5, 2b. Let's make sure we write that correctly, over log base 3 of 4, which is a. All right, another kind of puzzle problem here, where we're given certain conditions and we want to try to evaluate something. We know that log base b of 3 is 9. So this is what we're going to use, and that log base b of 2 is 7. So we're looking for those in this question of what we want to find. So this says log base b of 9, so we're looking for a way to how to get it to match up to be a 3. Well, we can simply rewrite this as 3 squared and then use that rule where the exponent comes out front. So we'll have 2 log base b of 3. We know the answer to that. And then next up we have log base b of 4. We're going to do the exact same thing here. We write 4 as 2 squared, and that 2 can come out front. So it's going to be 3 times that 2. So we're going to have 6 log base b of 2. Now we can go ahead and replace that. We know that log base b of 3 was really equal to 9. So we simply have 2 times 9 plus 6 times log base b of 2 was 7. So we have 18 plus 42. Let's go ahead and call that 60. So now we're on the expansion problems. So we're going to use those rules, and we're looking for quotients, products, and exponents. So I want you to start to see these as little templates. So the initial problem I see here is log, and it's understood it's base 10. We don't need to write that. It's the common log. I see this as a division problem. So I'm going to rewrite this using our rule for the log of a quotient and expand it to a difference. So that means here we're going to have log of 3x minus log of y squared. So now I should keep going and see that we have a product. So the log of a product I can expand. So the product will expand to addition of those two logs. So this will be log of 3 plus log of x. So we see that product there. And then over here we should recognize we have an exponent. We're going to be able to bring that out front. So this is going to be minus 2 times the log of y. And we've reduced each log as much as we can. There's nothing more to expand, so we're done with that one. In this problem, I see this as a multiplication problem. So I want you to see this as the log of something times something else. It's a little bit longer in this case. So, and it is base 6. That's not going to change anything as long as we're consistent. So we have log base 6. Our first piece was x plus, now here's our second piece, log base 6 of the square root of x minus 2. Now that square root may bother a few people, but just remember the rule that when you have the square root of a value, that's the same thing as that value to the 1/2 power. So now we're going to get an exponent involved here. So we're going to have log base 6 of x plus log base 6 of the quantity x minus 2 to the 1/2. And let's go ahead and use that power rule there where the 1/2 is going to come out as a product. So we're going to have log base 6 of x plus, and remember, here it is, this is going to come out front, is going to be 1/2 times log base 6 of x minus 2. Now some people want to go a little further because they see the log of x minus 2, but remember, the rules state that we can break down the log of a product, or the log of a quotient, or the log of something to a power. This is the log of a difference, subtraction. So we cannot go any further. So you cannot distribute logs. Logs are not distributive. So now we're looking to condense. We're going to put things together. There's different orders you can go in. I'm going to try to follow the order of operations whenever possible. So I will start inside parentheses here. And we're going to use the idea that if you see the sum of two logs, they can be put together as a product. So again, same base is one thing to recognize, the common log. So this is going to be the log of 3y. And I'm going to go ahead and bring everything else down. And I can just work my way right through. So I'm going to use these next two, log of 2 plus log of x. That is addition, so it comes together as multiplication. Log of 2x is of a single log. And we have minus the log of 3y. So now we see subtraction of two logs. That brings it together as a quotient or a division. So our order does matter, so the 2x is first, so that will be in the numerator, over the log of, we have the log of 3y, so we have 3y. And remember, this brings them to a single log. Do not make the mistake of writing log of 2x over log of 3y, because then you're saying that subtraction is the same thing as division. So we go from having two logs to a single log. We are condensing. B, we have a problem here. We can't put them together right away with the subtraction. So what we have to do is kind of pack things back in to a single log here. So that 1/2 has to go in and that 4 has to go in. And we're going to use that power rule there. So this is going to be ln of a to the 1/2, which as you recall can also be written as a square root, minus the ln of all of b plus 1, and that is going to be to the 4th power. And now that we have a subtraction of two logs, because it's the ln of something minus the ln of something else, we can say that's going to be a to the 1/2, which I'll write as square root of a, over whatever was here, which is b plus 1 to the 4th. And again, this can be written different ways. I think we're all right leaving it like that for now. Now we're going to move on to simple equations. These are very similar to what we did earlier because we're basically involves the log loop. So we see that we have 16 as our base, and we're going to raise that to the x. So 16 to the x is going to equal the argument, which is 64. And again, let's reduce this to bases. And in this case, 16 and 64, they're both related to a base of 4 and 2. I'll use 4 for now, just because it's easier for me. So this would be 4 to the 2x, and 64 is 4 to the 3rd. Bases match, so we can equate the exponents. So we have 2x equals 3, or x is equal to 3/2. Next up, this one seems to bother some people, and you'll see this in a minute. Our base is x, and we're going to raise it to the 3/2. And that's going to be equal to 8. Now, we can't break the x down anymore, so we have to remember something that you might have done earlier in the school year, that to solve a problem to a power, we raise it to the reciprocal power, and if we do it to one side, we do it to the other. So we're going to raise both sides to the 2/3 power. And in doing that, power to a power, this is x to the 1st, or simply x. Now we have 8 to the 2/3, so this means the cube root of 8, which is 2 to the 2nd power. Let's write that down in steps. So divided by 3 in the numerator here means the cube root of 8, and then we can raise that to the 2nd power. So that's going to be 2 to the 2nd power, or 4. Okay. Part C, I don't see a base here, so when there's no base for a log, it is a common log, which is used often in science. So we have a base of 10 that we're going to raise to the -2 to equal the x. So we have 10 to the -2 equals x. Many of you will rewrite this as 1 over 10 squared, which is 1 over 100, which is the value of x. All right, next up, the equations that are a little more involved. And the way I see it is there are two types of problems with the more involved equations. One where everything's in terms of logs, and the other type of problem when there's a constant involved. So first up is all the logs. So we'll look to reduce each side to a single logarithm. So we see addition here. So we're going to rewrite this as log base 4 of x times 2x minus 3, and that equals log base 4 of 2. So again here, you see you have the log of something is equal to the log of something else. So a must equal b. So we can continue on saying that what's in here, and I can go ahead and distribute this, which will be 2x squared minus 3x, has to be equal to 2 for those logs to match. So I should recognize this is a quadratic, so I'm going to use my different strategies for solving a quadratic. Set it equal to 0 and factor. If you struggle with some factoring, you can always go back and take a look at some of those videos. You can split the middle term here, or we can kind of think about it. The 2 is either going to go here or here because this has to be 2 times 1. So here I would have 4x and a 1x, so I want negative 4x plus 1x. So solving this would be x equals negative 1/2, x equals 2, but I need to pause for a minute. In the very beginning of the problem, there are domain restrictions. We can't log negative numbers or 0. So this answer, x, must be greater than 0. And here, we would say that 2x minus 3 must be greater than 0, which means 2x is greater than 3, or x has to be greater than 3/2. So this is our domain restriction. So if we get an answer outside that domain, we can't use it. So here where we see x equals negative 1/2, we can't use it. It's an extraneous solution. But x equals 2 meets our domain restrictions, so that is our final answer. All right, next up, we see we have logs on one side equals a constant, so we're just going to simplify this left-hand side. And if I see subtraction, we're going to write this as a quotient. So log base 3 of x plus 4 over x minus 3 equals 3. Now, once we do this, notice that we can use our log loop. That 3 to the third power is going to equal the argument, x plus 4 over x minus 3. All right, once we have that, let's just rewrite this a little bit more. We're going to have x plus 4 over x minus 3, and 3 to the third is 27. So to solve these, we could just multiply both sides by x minus 3. Some people like to say over 1 and cross multiply. So either way is fine. So I'd have 27 times x minus 3, which is 27x minus 81. And that will equal x plus 4. So we're just solving a linear equations. We'll subtract x from each side and have 26x. We'll add 81 to both sides. We'll have equals 85. So our final answer is simply 85 over 26. All right, we're down to our last question here. It's the idea of looking at a log equation or possibly a graph. First up says to find the domain. So the domain of a log equation is always taking the argument right here and saying it has to be greater than 0. So we're just going to simply say 2x minus 1 is greater than 0. 2x is greater than 1. X is greater than 1/2 is our domain. And if you need that in interval notation, that would be from 1/2 to infinity, written like that. F of 14 just means we're going to let x equals 14 and solve it. So that means our answer is going to be log base 3 of 2 times 14 minus 1. 2 times 14, 28. So we're going to have 28 minus 1. So we're going to have log base 3 of 27, which again, we might know this by now. 3 to some power is 27. And if we don't know it, we can just say, okay, this is always going to equal our answer. In our case, we're going to say y. So it'd be 3 to the y is 27. And 27 you would rewrite as 3 to the third. Equating exponents gives you an answer of y equals 3. Or more specifically, f of 14 is equal to 3. Last question says find the x-intercept. So remember, x-intercepts are when y equals 0, or in our case, f of x equals 0. So we're going to say that the equation log base 3 of 2x minus 1 equals 0. So again, we have it reduced to the log of an argument, so we can use our little log loop. So we're going to say 3 to the 0 is equal to the argument 2x minus 1. 3 to the 0 is 1. Add our 1 over, divide by 2. 2 equals 2x. So x equals 1. So that's all there is to it. Just be careful writing things out and applying those properties. It's always helpful to have them written in front of you while you are solving. I hope that helps.